Welcome to The Explainer. Today, we're diving into the fascinating, and honestly kind of invisible, world of process dynamics. Specifically, we're going to look at how to tame those wild dynamics using control structures. You know, if you've ever wondered how massive chemical plants or huge manufacturing facilities keep from this spiraling into total chaos, well, you're in the right place. Let's unpack the engineer's toolkit together and see exactly how they design control configurations for maximum stability and safety.
Okay, I want to kick things off with this quote straight from our source material because it really sets the stakes perfectly. The operation of modern industrial plants would be very difficult, if not impossible, without automation. Think about that for a second. We're talking about thousands, literally thousands of process variables, temperatures, flow rates, pressures, and they all need to be kept precisely within very specific limits. Why? Well, because in industrial engineering, we are constantly battling this one recurring villain: the deviation from the set point. When temperatures randomly spike or pressures suddenly drop, things go wrong, fast. So our goal today is to learn exactly how engineers fight back against that villain.
All right, let's dive into this. Here is our roadmap for this explainer. First, designing the structure, then feedback control, feed-forward control, ratio control, cascade control, and finally, variable pairing.
Part 1. Designing the control structure.
So before you can even think about tuning a single controller, you've got to make these crucial architectural decisions that are going to dictate the safety and efficiency of your entire plant. When engineers look at a typical industrial approach to a multi-loop control strategy, they're essentially drawing up a high-level blueprint using three main steps. First up, you've got to select your control variables, the stuff you actually care about, like product quality or throughput, and your manipulated variables, which are the valves or inputs you can actually physically tweak. Second, you select the pairings, like which valve is going to control which temperature. And third, you specify the types of feedback controllers you're going to use, like your standard PID controllers. This right here, this is your absolute foundation.
Now, you might be wondering, how do you actually make those decisions? Well, historically, there's been a bit of a divide. On one side, we've got the traditional approach. This relies super heavily on engineering insight, experience, and heuristics. You basically build it, install it, and then rely on controller tuning, which is essentially just adjusting settings by trial and error out on the plant floor. On the flip side, we have the model-based approach. Now, this relies on serious mathematical precision. You develop a dynamic model of the process first, and then use that mathematical model as the basis for designing your controllers. It's just a much more calculated way to ensure stability long before you ever open a valve in the real world.
Moving on to Part 2, the reactive approach, feedback control.
Let's slot the first and honestly most fundamental tool into our blueprint. The definition here is key. Feedback control measures the controlled variable, compares it to the desired value, and then uses that measurement to adjust the manipulated variable. It's like, if your room's too cold, the thermostat measures that cold air and kicks on the heater. But notice what's missing from this definition. It doesn't actually measure the disturbance itself. It only measures the result of that disturbance on the controlled variable.
Right. So the absolutely crucial point here is this: feedback control reacts after the upset occurs. That is its main vulnerability. Because the disturbance variable is unmeasured, the system is essentially blind to the incoming problem until our villain, that deviation from the set point, has already attacked. It fights the deviation retroactively. Now, don't get me wrong, it's incredibly reliable, but by definition, it means your process has to experience an error before it can actually step in and fix it.
Which brings us to Part 3. Anticipating upset with feed-forward control. So what if your process just can't afford that error? What if a sudden temperature drop ruins a massive, incredibly expensive batch of chemicals? Well, feed-forward control flips the script to proactively solve this. Instead of measuring the controlled variable, it measures the disturbance variable online. Once it sees a disturbance coming, say a sudden drop in incoming feed temperature, it takes corrective action immediately, before the controlled variable is even upset. It is a hugely powerful strategy for regulatory control because it anticipates the chaos before it hits. And this brilliantly illustrates the core difference between these two foundational strategies. Just look at this side by side. Feedback measures the controlled variable but completely ignores the disturbance. Feed-forward, on the other hand, measures the disturbance but ignores the controlled variable. Because feed-forward doesn't look at the final output, it relies heavily on having a really accurate process model. In industrial reality, because it's completely uneconomical to measure every single little disturbance, engineers usually combine both. They use feed-forward to catch the big measured disturbances and feedback to kind of clean up the unmeasured ones. Best of both worlds, right?
Part 4. Perfect harmony through ratio control.
Now we're building into the more specialized tools. Ratio control is actually a very specific, widely used flavor of feedforward control. And the core formula here is beautifully simple. R equals U over D. That means the ratio equals the manipulated variable divided by the disturbance variable. Instead of trying to control individual flow rates completely independently, the controller's main objective is to just lock in the specific mathematical relationship between the two.
To ground this math in reality, think about continuous blending operations. If you're mixing two liquids together to create a specific chemical product, you don't necessarily care if the total volume fluctuates a bit, but you absolutely care that the ratio of chemical A to chemical B remains exactly perfect. If the unmeasured disturbance flow increases, the manipulated flow must automatically increase to match that exact ratio. It's all about keeping things perfectly proportional.
Part 5. Nested loops, also known as cascade control.
Okay, so when simple feedback just isn't fast enough and feed-forward isn't possible, maybe because you just can't measure the disturbance, we arrive at a much more complex strategy. Now, what's really interesting about this slide is if we look closely at this furnace schematic from our sources, we can clearly see the nested nature of this strategy. We're trying to control the hot oil temperature leaving the furnace, but instead of just having one single temperature sensor directly controlling the fuel gas valve, we've actually added a second measurement point. We have a temperature sensor on the oil, and we have a pressure sensor right there on the fuel gas line.
And honestly, this is the genius of cascade control. You have a primary controller looking at your main objective, the hot oil temperature. But its output doesn't go straight to a valve. Instead, its output serves as a set point for a nested secondary controller. That secondary controller is the one that actually handles the fuel gas pressure. Why do it this way? Because if the fuel gas pressure suddenly drops, the secondary loop detects it and opens the valve immediately. It reacts to the disturbance incredibly quickly, fixing the fuel pressure long before that massive volume of hot oil ever has a chance to change temperature. It's like having a lightning-fast reflex built inside your main system.
Finally, Part 6. Pairing variables and managing interactions.
So what happens when you put multiple loops into a single multi-input, multi-output process? I mean, when a set point change in one loop accidentally causes the controlled variable in another loop to change, you've got process interaction. It's like a giant puzzle. If you pair the wrong variables together, your entire plant can become completely unstable. To solve this, engineers use something called the relative gain array, or RGA. Developed by Bristol, the RGA is basically the ultimate matrix tool used to measure process interactions. It calculates a relative gain, represented by the Greek letter lambda, which is the dimensionless ratio of the open loop gain to the closed loop gain.
This matrix is super cool because it shows exactly how the RGA value dictates whether a system achieves stability or just spirals into chaos. If your lambda value is exactly 1, that is an ideal pairing. It means there's no interaction, or maybe just a one-way interaction from other loops. But look at that second row. If lambda is 0 or any negative number, the recommendation is absolute. Do not pair. Pairing a manipulated and controlled variable with a negative relative gain will result in closed-loop instability. Your system will literally fight itself, no way around it. And if lambda is a fraction between 0 and 1, well, you've got to proceed with caution, because interaction definitively exists. The RGA matrix basically cuts through all the guesswork and tells you exactly how to safely wire your plant's brain.
We've covered some incredible ground today, from the basic reactive feedback loop to the anticipating feed-forward loop, through the intricate nested layers of cascade control, all the way to the absolute mathematical certainty of the relative gain array matrix. But I want to leave you with a provocative thought as you look at your own theoretical processes. If feed-forward anticipates the disturbances we know about, and feedback reacts to the ones we don't, what unseen disturbances is your control system completely missing? What vulnerabilities are hiding right there in the spaces between your sensors? Think about that, and I'll catch you next time on The Explainer.